Dear students, now we are going to see the subject linear integrated circuit. The subject code is EC3451. Under that, the topic is instrumentation amplifier. On completion of this instrumentation amplifier, student will be able to explain the working of instrumentation amplifier. Some of the examples of instrumentation amplifiers are measurement and control of temperature, humidity, light intensity, water flow, etc. These physical quantities are usually measured with the help of transducers. The output of transducer has to be amplified so that it can derive the indicator or display system. This function is performed by an instrumentation amplifier. The important features of an instrumentation amplifier are high gain accuracy, high CMRR, that is common mode rejection ratio, high gain stability with low temperature coefficient and low output impedance. The simple differential amplifier circuit using single op-amp is shown in figure. So in differential amplifier, two inputs V1 and V2 are applied to the inverting and non-inverting terminal of the operational amplifier, and the feedback is done through the resistance R2. The output V0 is given by V0 is equal to R2 by R1 into V1 minus V2. So the improved instrumentation amplifier is shown in this figure. The first stage, it has two operational amplifier. This output is given to the second stage operational amplifier. So voltage at the input terminal of op-amp A3 is given by R2 into V1 divided by R1 plus R2. Using superposition theorem, the output V0 is equal to minus R2 by R1 into V1 minus V2. Since no current flows into the op-amp, the current I flowing in the resistor R is given by I is equal to V1 minus V2 by R, and passes through resistor R is given by V1 equal to I into R plus V1. That is V1 dash equal to R divided by R dash by R, V1 minus V2 plus V1. V2 dash is equal to I into R plus V2. Similarly, V2 dash is equal to minus R dash by R, V1 minus V2 plus V2. Substitute this equation 2 and 3 in 1. So output V0 is equal to minus R2 by R1 into 1 plus 2R by R into V1 minus V2. In the circuit, the source voltage V1 sees an input impedance of R3 plus R4. Its typical value is 101 kilo ohm, and the impedance seen by the source V2 is only R1. Its value is 1 kilo ohm. This low impedance may load the signal source heavily. The op-amp A1 and A2 have a differential input voltage as 0. For V1 equal to V2, that is under common mode condition, the voltage across R will be 0, as no current flow through R and R dash the non-inverting amplifier. A1 acts as a voltage follower, so its output V2 dash is equal to V2. Similarly, op-amp A2 acts as a voltage follower, having an output V1 dash equal to V1. However, if V1 not equal to V2, the current flows in R and R dash, and V2 dash minus V1 dash should be greater than V2 minus V1. The difference gain of this instrumentation amplifier R, however, should never be made 0, as this will make the gain infinity. To avoid such a situation in a practical circuit, a fixed resistance in series with a potentiometer is used in place of R. That is, the instrumentation amplifier using a transducer bridge is shown in this figure. The circuit uses a resistive transducer whose resistance changes as a function of physical quantity to be measured. The bridge is initially balanced by a DC supply voltage VDC so that V1 equal to V2. As the physical quantity changes, the resistance RT of the transducer also changes, causing an unbalance in the bridge, that is V1 not equal to V2. This differential voltage now gets amplified by 3 op-amp differential instrumentation amplifier. Applications of instrumentation amplifier with transducer bridges: temperature indicator, temperature controller, light intensity meter. So some of the quiz question: what are the characteristics of an instrumentation amplifier? high input resistance, low noise, high CMRR, all the above. Answer is all the above. Which one of the following instrumentation amplifier is a type of monolithic in amplifier? AD8250 and AD8251 are the monolithic instrumentation amplifier. Thank you.